Hello, and welcome to our Analytical Foodies bite-sized webinar series. This series will provide hints and tips to help you be successful with your multi-residue analyses. My name is Emer McCall, and I'm a Principal Market Development Manager here at Waters Corporation. The topic of this episode will address a few calculations useful in determining matrix effects. So before we get into the calculations themselves, let's just cover some of the commonly used terms. What are matrix effects? Matrix effects are where the MS response of an analyte differs between standards prepared to the same final concentration in solvent and food commodities. For many of us running mass spectrometry-based multi-residue methods, these effects are an everyday occurrence. Taking electrospray ionization as an example, matrix effects begin when an injected sample consisting of analytes, matrix, mobile phase, and additives arrive into the ionization source through the capillary. The presence of the matrix, which is everything other than the analytes of interest now in the source, has an impact on the ionization of our analytes. This is because the matrix components impact the efficiency of droplet formation or the droplet evaporation, which are essential for efficient ionization. This in turn, of course, affects the amount of charged ions in the gas phase that reach the detector. The impact on ionization efficiency can result in two effects. One, where the analyte's response in a food sample is reduced relative to that in solvent. Or second, where the analyte's response in a food sample is amplified relative to the analyte's response in solvent. There's a number of ways in which we can measure these different effects. All methods, of course, require solvent-based standards and standards prepared to the equivalent final concentrations in the sample types under analysis. A simple comparison of the responses achieved for the analytes across standards allows for the effects to be quantified, and this is shown here for the matrix effect factor calculation on screen. When carrying out any analyses to determine the matrix effects, we need to also consider the method's extraction efficiency of the analyte. This should be determined separately to matrix effects from analytical experiments or referencing published methodologies. To avoid overestimation of ion suppression, we typically employ matrix-matched standards, which means we prepare our samples in accordance with the relevant homogenization, extraction, and cleanup procedures, and then we spike this extract to the required concentration. This ensures that any analyte loss is due to the effects of matrix rather than the sample preparation procedure itself. By running a number of standards prepared in solvent and as matrix matched, we can readily calculate the matrix effect factor. This process is further simplified within MassLynx. Prior to processing our matrix and solvent data, we can assign the relevant sample types of solvent for solvent standards and blank for our matrix match standards, and simply process the dataset. Once processed, we can select the matrix factor tool within TargetLynx and look at the summary table for a quick estimate of the matrix effects observed for the method. In this example, we can see that fipronil spiked at levels equivalent to 2 micrograms per kilogram in egg and solvent show an average of 0.71 matrix effect. From this brief study, we now understand that fipronil is being suppressed in the egg sample, and so reliable quantitation during routine analysis may be impacted. Of course, another common way of reporting matrix effects, rather than as a factor, is as a percentage. Reporting matrix effects as a percentage provides an absolute value, allowing for easier translation of the amount of suppression or enhancement. On screen, we see two options to quantify percentage effects. On the left-hand side of the screen, we see a slight variant of what we've just discussed, where we're comparing solvent-based and matrix match standard at a fixed concentration, made absolute, and converted to percentage. In some instances, the effects observed by matrix may vary with the concentration of analytes. For this reason, it can be good practice to calculate matrix effects across the intended working concentration range of your method. The easiest way to do this is shown on the right-hand side of the screen, where calibration series are prepared to equivalent concentrations in both solvent and matrix match standards. Taking the slope of each calibration line, we can slot these values into the equation on screen. Because we've made all results absolute, data interpretation is simplified. Ion suppression is declared if the calculated value is less than minus 100%, while ion enhancement is present if the calculated value is greater than 100%. For results around 100%, they are considered negligible. However, if effects of greater than 20% are calculated, determining either enhancement or suppression, it's considered best practice to take action and correct these effects. This will ensure accuracy of results during routine analysis. So that's a lot of information. Let's see what it all means with a couple of practical examples. Firstly, let's stay with the fixed concentration calculation, where we've spiked Ketcher's extraction solution and a Ketcher's extracted egg on the left and soybean on the right. All samples are spiked equivalent to the targeted maximum residue level. Before we actually start calculating the matrix effects using the equation, we can see in the images how the response of fipronil on the left and picolinophen on the right in solvent differ from the same concentration in their respective matrix-matched extracts. Looking at these overlaid peaks, we can safely assume that fipronil is being suppressed by eggs, while picolinophen is being enhanced by soybean extract. These assumptions are supported with a quantified value of the effects using the B over A equation, where nearly 30% suppression and 40% enhancement is determined for fipronil and picolinophen respectively. Taking the same samples, calibration series were prepared over the required working range to equivalent concentrations in both solvent and the relevant sample type. Again, before getting into any calculations, we see a similar trend in response when both solvent and matrix-matched data are overlaid. Of course, quantifying the effects is required to understand what corrective action, if any, is required to ensure a reliable method is robustly developed and maximize lab efficiency during routine analyses. Inputting the slope of each line into the equation, we calculate similar effects across the working range for both fipronil and picolinophen as just reported at the fixed MRL concentration. As we've just seen, overlaying our data allows for very informative observations to be made. One more example of an image providing additional intelligence is shown here, where we're looking into full scan background of our chromatographic gradient. With many of our multi-residue methods run on tandem quadrupole mass spectrometry technology, the typical acquisition mode is multiple reaction monitoring, or MRM. This mode offers good selectivity for targeted masses. However, we can sometimes miss what is going on in the background. During method development, however, we can acquire full scan data simultaneously with our targeted MRMs. This acquisition mode is termed radar within waters, and radar can provide visual aids to understand what matrix components are eluting over the chromatographic gradient, and also allows spectral information to be extracted across regions of interest, providing good qualitative and quantitative data. In addition to calculating matrix effects, acquiring radar data during method development enables more informed inferences to be made on the data and our method. So putting radar into use, we can see how the profiles of our full scan data and response of the analytes, overlaid here in blue, varies across commodity groups and matrix complexity. In all examples, we've run crude Ketcher's extracts, all on the same LC gradient. The variability shown here across the 6 sample types summarizes well the occurrence of matrix effects that may be interfering in our analyses. As we look to quantify matrix effects in our methods, some key points discussed in this episode are summarized. By considering matrix effects during method development, your method's reliability and future sample throughput may be enhanced. If you discover your analytes are affected by greater than 20%, further action may be required. A number of options to reduce and compensate for matrix effects are discussed in another episode of this series. Thanks for viewing this episode. More episodes in the Analytical Foodies Bite-Sized webinar series are available on waters.com.